Welcome to NAND to Tetris Part 2. NAND to Tetris is the name of a computer science educational adventure in which we build a complete modern general-purpose computer system, hardware and software from the ground up. Because this is quite a substantial journey of discovery, we decided to split it into two separate and standalone courses. In the first course, which in Coursera is simply called NAND to Tetris, we start with the most elementary and sort of primitive logic gate conceivable called NAND, and using a series of 6 hardware construction projects, we build a computer platform which we call HEC. And then in the second course, in NAND to Tetris Part 2, in this course, we start with a computer system, hardware and software. Welcome to NAND to Tetris Part 2. NAND to Tetris is the name of a computer science educational adventure in which we build a complete modern general-purpose computer system, hardware and software from the ground up. Because this is quite a substantial journey of discovery, we decided to split it into two separate and standalone courses. In the first course, which in Coursera is simply called NAND to Tetris, we start with the most elementary and sort of primitive logic gate conceivable called NAND, and using a series of 6 hardware construction projects, we build a computer platform which we call HEC. And then in the second course, in NAND to Tetris Part 2, in this course, we start with the HEC platform as a point of departure, and then we build on top of it a virtual machine, a compiler, an operating system, and all the systems which are necessary so that we'll be able to write high-level object-based programs on this bare-bone hardware. That's what we do in the second part of the NAND to Tetris journey. The creators of NAND to Tetris are Professor Noam Nissan, who works at the Hebrew University of Jerusalem, and myself. My name is Shimon Shoken. I work at the IDC Herzliya. And as you see from these pictures, both Noam and I enjoy getting into and playing with the most elementary and fundamental building blocks of applied computer science. And I must tell you that the deeper we look into computer science and mathematics for this matter, the more beauty that we discover. And as you take the NAND to Tetris courses, you will share with us exactly the same profound feeling. So here is the big picture of NAND to Tetris, and what we see here are the two endpoints of our journey. At the bottom, we see the bare-bone hardware, which is capable of nothing more than detecting between two different signals, zeros and ones, and processing these signals in remarkably clever ways. And at the top of the journey, we see some human high-level programmer or an entrepreneur who have all sorts of lofty thoughts and fantasies about developing computer games and search engines and airline reservation systems and whatnot. And the question, of course, is how do you bridge the gap between the abstract thoughts of the high-level programmer and the bare-bone hardware that can do nothing more than process zeros and ones? Well, bridging this gap is what NAND to Tetris is all about. And as you see, we do it in several different well-defined stages, and each one of these stages entails one or more programming projects, and once again, we split it into two different courses. So in NAND to Tetris Part 1, also called simply NAND to Tetris in Coursera, we begin with many instances of the NAND generic gate, and using these gates, we build some elementary logic gates like AND, OR, NOT, XOR, multiplexers, and so on. Then we put these gates together, and we build memory systems, ALU, CPU, and the entire HEC chipset. Then we assemble these chips together, and we create what is known as a classical von Neumann hardware architecture, and we end this course with writing an assembler for this particular computer. And so at the end of this process, voila, we have a computer, which we call HEC. Now, at this point, NAND to Tetris Part 2 kicks in. And in this course, we treat the HEC computer platform as an abstraction. We don't care about questions like how the CPU was constructed and how registers are built from lower-level data flip-flops. We don't care about all these details because we have a computer, which for us is a black box abstraction, and we're going to interact with this computer through its interface, which is machine language. But actually, it's more convenient to think about the second part of this course top-down. So let's shift our attention to the left side of the screen and focus on what happens in the process of writing high-level programs. And this, by the way, is exactly what you guys do when you write programs in Java or Python or C#. You don't care about all the other parts of the computer. You just focus on the high-level programming task. Now, in NAND to Tetris Part 2, we're going to introduce a high-level language called Jack, which is a simple version of Java and Python, C#, and it's a language that if you know any one of the languages that I just mentioned, you can learn it in something like 1 hour of learning, and then you can write very nice programs in the Jack language. Let me show you some examples of programs that our students have written in previous versions of this course. So here's a program in which we play Pong, and that's a program that the student wrote in order to teach typing skills in an interactive and engaging computer game. Here is Space Invaders. Here is Sokoban, a famous game that came from Japan. Here is a Bouncing Ball, a very nice animation. And here is a Roar game. And of course, many students developed all sorts of versions of Tetris. By now, thousands of students have taken these courses, and therefore there are many examples of cool Jack programs out there. And here's one program that I wrote. And in this program, we see some two-dimensional points, and the program constructs these points and manipulates them using all sorts of algebraic manipulations. So let's take a look at this program. What we see here is the Jack code that actually generated some of the output that you see in front of you. It begins with a class called point, which implements the two-dimensional point functionality. And then we have another class called main that uses the services of the point class in order to create and manipulate some points on the screen. So that's how the Jack code looks like, and I think that you will agree with me that it looks very similar to other languages like Java and Python. And in fact, in the third week of this course, you guys are going to write some programs like this one using Jack, and we want you to do it in order to get a feeling of the language for which we will have to develop a compiler later on in the course. In particular, as you know, when you want to execute a program that you wrote, the first thing that you have to do is compile it. So here's our compiler. And just like other compilers like those of Java and C# and to a certain extent Python, our compiler does not translate the source code directly into machine language, but rather it translates your source code into an intermediate language called VM code, which is designed to run on an abstract virtual machine. Now, it goes without saying that I don't expect you guys to understand any of the details of what you see here, and we're going to give you all the necessary background and all the techniques which are required throughout the course. At this level, I just want you to get the spirit of what's going on. So here's how the compiler works. It goes through your source code, and if we focus on one particular command, for example, the command that creates a new point with coordinates x equals 1 and y equals 2 and stores the address of this object in P1, well, this code is going to be translated by the compiler into 4 VM commands, as you see at the right-hand side of the screen. Now, you guys are going to write this compiler under our guidance, of course, in weeks 4 and 5 of this course. Now, the resulting code that you see here, which is very similar to what is known as Java's bytecode, also similar to what is known as IL in the world of .NET and C#, well, this code is also an abstraction. It is designed to run on some imaginary computer, a virtual machine. In order to make this abstraction concrete, we have to translate this code further into machine language. And the machine language that we're going to use is the native code of the heck computer. And you see it here in front of you. This is heck assembly language. So here's an example of how this VM translator works. It takes, let's say, the first command in your VM program, which is a push1, a typical stack-oriented command. And once again, we'll discuss all this stuff in the course. I don't expect you to even know what a stack is. But it takes the first push command and translates it into what comes out as 7 or 8 different machine-level instructions. And once we have these instructions generated, we can load them into the computer, and finally, the program will start executing. So that's what you guys are going to do in the first 2 weeks of the course. You will develop a VM translator, which is quite similar to Java's Jvm and to Microsoft's CLR. Everything that we do in this course follows the modern paradigms of software engineering and lets you guys to sort of get into the most important ideas behind every one of these tools. Now, there's one piece which is missing in this puzzle, and this is the operating system. Because you see, you cannot write a high-level language these days without using the services of the host operating system. Because there's so many things that you have to handle: graphics, animation, reading input from the keyboard, managing your objects in memory. Who's going to do all these things? You? There's no way that we can require high-level programmers that have so many problems of their own to take care of all these nitty-gritty details. For this, we use an operating system. So in assembly language, the first thing that you have to do is compile it. So here's our compiler. And just like other compilers like those of Java and C# and to a certain extent Python, our compiler does not translate the source code directly into machine language, but rather it translates your source code into an intermediate language called VM code, which is designed to run on an abstract virtual machine. Now, it goes without saying that I don't expect you guys to understand any of the details of what you see here, and we're going to give you all the necessary background and all the techniques which are required throughout the course. At this level, I just want you to get the spirit of what's going on. So here's how the compiler works. It goes through your source code, and if we focus on one particular command, for example, the command that creates a new point with coordinates x equals 1 and y equals 2 and stores the address of this object in P1, well, this code is going to be translated by the compiler into 4 VM commands, as you see at the right-hand side of the screen. Now, you guys are going to write this compiler under our guidance, of course, in weeks 4 and 5 of this course. Now, the resulting code that you see here, which is very similar to what is known as Java's bytecode, also similar to what is known as IL in the world of .NET and C#, well, this code is also an abstraction. It is designed to run on some imaginary computer, a virtual machine. In order to make this abstraction concrete, we have to translate this code further into machine language. And the machine language that we're going to use is the native code of the heck computer. And you see it here in front of you. This is heck assembly language. So here's an example of how this VM translator works. It takes, let's say, the first command in your VM program, which is a push1, a typical stack-oriented command. And once again, we'll discuss all this stuff in the course. I don't expect you to even know what a stack is. But it takes the first push command and translates it into what comes out as 7 or 8 different machine-level instructions. And once we have these instructions generated, we can load them into the computer, and finally, the program will start executing. So that's what you guys are going to do in the first 2 weeks of the course. You will develop a VM translator, which is quite similar to Java's Jvm and to Microsoft's CLR. Everything that we do in this course follows the modern paradigms of software engineering and lets you guys to sort of get into the most important ideas behind every one of these tools. Now, there's one piece which is missing in this puzzle, and this is the operating system. Because you see, you cannot write a high-level language these days without using the services of the host operating system. Because there's so many things that you have to handle: graphics, animation, reading input from the keyboard, managing your objects in memory. Who's going to do all these things? You? There's no way that we can require high-level programmers that have so many problems of their own to take care of all these. Reading input from the keyboard, managing your object, and this is the operating system. Because you see it's behind every one of these tools. Now, there's one piece which is missing in this puzzle, and this is the operating system. Because you see, you cannot write a high-level language these days without using the services of the host operating system. Because there's so many things that you have to handle: graphics, animation, reading input from the keyboard, managing your objects in memory. Who's going to do all these things? You? There's no way that we can require high-level programmers that have so many problems of their own to take care of all these nitty-gritty details. For this, we use an operating system. So in week 6 of the course, we're going to develop exactly such basic operating system under our guidance. So here again is the big picture of Untitled Chapter Part 2 with the projects laid out on the roadmap. And many people ask us, how can you possibly cover so much material and build so many important fundamental systems in applied computer science, in no more than 6 or 7 weeks of instruction? Well, we have a secret sauce, and the secret sauce is our course methodology. In particular, you have to understand that, first of all, we are going to teach you all the necessary computer science knowledge which is necessary in order to build all the systems which are described in this course. You don't have to bring from home any previous knowledge except for some basic programming skills. We'll provide all the necessary algorithms, data structures, programming tricks and hacks and so on. Also, we're going to provide you with some very useful software tools that will make your life easy. For example, before we ask you to implement the virtual machine yourself, we will give you a VM simulator that will enable you to play with an animated virtual machine and understand exactly what has to be done in the actual project that you have to develop. Also, in this course, Noam and I are going to play the role of the system architects, and you guys are going to be the software developers who actually implement the specifications that you get from us. So we're going to supply you with elaborate and well-explained APIs and blueprints and design documents, and so there will be no uncertainty and confusion whatsoever. You will know exactly what you have to do to the letter. And in addition with all these design documents, we're going to also provide you with a huge pile of test programs and test files and test scripts so that you will be able to test your work, or I should say unit test what you do in a very low resolution. Something like every 10 or 15 lines of code, you will have a test that you will be able to apply to what you wrote and convince yourself that what you've done is good and that you can continue to go to the next stage in the development. And the most important feature of our course methodology is that the course is a lot of fun. It is thrilling to build a computer from the ground up, and you're going to enjoy it tremendously. And I must say that by now, thousands, if not tens of thousands of people and self-learners and students have already taken Nanto Tetris courses, and with very few exceptions, all of these guys are very happy campers. And so that's the big picture of Nanto Tetris Part 2 and the course methodology. The course is going to last 7 weeks, and in every one of these weeks, we're going to have a set of video lectures that will take you something like 3 hours to view. Then you will also have a project, a programming project that you have to implement, and there's also a book chapter that you are welcome to read, but it's not required. The textbook that accompanies this course was written by Noam and myself. It was published by MIT Press, and it's an optional reading. If you want, you can use it, but you don't have to. Altogether, the weekly workload is going to be something between 10 to 20 hours of work, depending on which week we're in. And I must say that the word week is somewhat weak, W-E-A-K, in the sense that if you want your week to last 10 days or 14 days, that's perfectly okay with us. You should work on these projects at your own pace, and you are the captain of the ship. We just give you some guidelines, but you decide exactly how you want to drive it. And you will need some self-discipline and try to complete these projects within the course schedule. But once again, if you slip, that's fine with us. The most important thing is to complete the projects and learn the underlying ideas and techniques. The prerequisites of this course are quite minimal. We expect that you have some programming ability at the level which is acquired in typical introduction to computer science courses. So you have to know either Java or Python. You have to know the basic techniques and skills of object-oriented programming. If you have this basic knowledge, then you're welcome to take Nanto Tetris Part 2. It is also recommended, but certainly not required, that you will take Nanto Tetris Part 1. In fact, the two courses are so independent of each other that you can take them in reverse order, if you will. But of course, we recommend that you take Part 1 first, Part 2 second. But once again, you don't have to. You can start from scratch with Nanto Tetris Part 2. Now, in closing, I made a list of some of the topics that are going to be covered in this course. And it's quite, I think, mind-boggling to see how many subjects we are going to visit in Nanto Tetris Part 2. And the exciting thing about this laundry list here is that we're not going to wave our hands too much about any one of these concepts. We'll explain them, of course. There'll be no, as I said, no uncertainty and no confusion. But every item that you see in this list is something that you will learn hands-on, because it will come up in the context of building a system, something that you're going to do with your own hands. So this, in a nutshell, is the contents of, once again, most of the contents of this course. And as you go through this course, you will become a significantly more sophisticated, enlightened, and confident software developer. Because you see, right now, I assume that you may have some very good high-level programming skills, but you have all sorts of doubts and some uneasy feelings about how the compiler works, what exactly is the virtual machine, how my program interacts with the operating system, and how all this gestalt works together. Well, Nanto Tetris sheds light on all these questions, and as you get this knowledge, once again, you become a much more sophisticated developer. In addition, you will be exposed to numerous, I should say, the most important ideas and techniques in applied computer science, and finally, you will become a richer person. Not necessarily financially richer, although I think that this course will certainly contribute to your career prospects. You will become richer intellectually, because through this course, you will connect to the soul of the machine. You will connect to the soul of the most important machine that mankind has built, at least in modern times. And connecting to the soul of this machine is what Nanto Tetris is all about. So thank you for sitting patiently through this course overview, and the next thing that we'll do is discuss Project Zero. The first project in this course, Project Zero, is so trivial that it hardly merits the word project, but so be it. In this project, we have to do two things. First of all, we request that you download the Nanto Tetris software suite and put it on your personal computer. And the second thing that you have to do is submit a file to the Coursera website. And we want you to do it just that you go through the motions of compressing and submitting a file, as we'll describe in a moment. So the first thing that we have to do is download the Nanto Tetris software to your PC. And in order to do so, we request that you go to this website, www.nantotetris.org, locate the software page as we see here. Within the software page, you have to locate this particular link. And once you click this link, a file named nantotetris.zip is going to be downloaded to your PC. Once you get this file, we request that you extract it on your PC, and the result will be a directory or a folder called NAND2Tetris. We recommend that you put this folder on your desktop, and we're going to use this folder obviously extensively throughout the course. In particular, if you look into this folder, you will see that it is divided further into two subfolders named Tools and Projects. By the way, before I go on, I have to say that even if you took NAND2Tetris Part 1, we still highly recommend that you re-download the NAND2Tetris software to your PC, because we are making changes in the software as we go along, and it is quite possible that you don't have the most up-to-date version of our stuff. So please download the software again before you start NAND2Tetris Part 2. So going back to this folder, you will see there two subfolders named Tools and Projects. Tools contains all sorts of useful software tools that will help you go through NAND2Tetris Part 1 and Part 2. And the projects consist of 14 directories named 00 to 13. Now, what you see here are all the tools and projects and resources which are needed to take both NAND2Tetris Part 1 and NAND2Tetris Part 2. In NAND2Tetris Part 2, we're going to focus on these tools and projects only, and all the other stuff is irrelevant to NAND2Tetris Part 2. As you see, Project 4 has a dashed outline because it's an optional project in NAND2Tetris Part 2, and I will have more to say about it as we go along very soon in one of the next units. All right, so that's the structure of the NAND2Tetris folder. Once again, we recommend that you put it on your desktop. And going back to Project 0, let us assume that you have already downloaded, extracted, and took a look at this NAND2Tetris folder. What do you have to do next? Well, the next thing you have to do is within the NAND2Tetris folder, you have to locate this file, which is named file.txt. And then the only thing that we want you to do with this file is submit it as is. You see, we want to make sure that we go through the very simple mechanics of submitting a file. And once you will do this, we'll give you feedback that we got this file, and then we can actually start moving with the course itself. So here's what we want you to do. We want you to take file.txt and compress it into project0.zip. And once you have this zip file made, we request that you submit it to the Coursera course website. Just follow the instructions. There will be written instructions on how to submit Project 0. Just follow them and submit the file to us. Once we'll get this file, we'll send you an acknowledgement that we got it. And then, once again, we can start the real projects in this course. So this has been the overview of Trivial Project 0. And the next units that we're going to explore will deal with machine language. Welcome to Module 0 of NAND2Tetris Part 2, in which we're going to talk about machine language basics. Now, a note to graduates of NAND2Tetris Part 1. Even if you feel completely competent with hack programming and low-level programming, you still have to bear with me at least through this preliminary unit, and then you can decide how much more you want to take from this primer, because almost all the material that we're going to cover in this module is something that we covered already in Part 1. But once again, bear with me until the end of this unit. All right, so here is the big picture of NAND2Tetris Part 2. Here are the various modules that we're going to go through throughout the course, beginning with Module 0. Now, Module 0 deals with a very exciting interface in applied computer science, and this is the point where hardware meets software. In particular, we meet the hardware, or we use the hardware platform through its interface, which is machine language. And we need this machine language, and we need Module 0 in order to set the stage and build a foundation for the next two modules in which we're going to build the computer's virtual machine. And in order to explain this delicate handshake, take a look at this slide here. And you will notice that what we have here is some VM code written in a language called the virtual machine language, of which I don't expect you to understand anything. This is something that we're going to describe later on. But notice that we're going to discuss this language as well as the task of translating programs written in this language into machine language, into assembly. So in particular, the VM translator is going to be a program that you guys will write under our guidance in some language like Java or Python. This program will treat the VM code as input, and it will start marching to this input and generating assembly code from it. So for example, it will start with push 1 and generate the assembly code that you see here. Then it will go on to parse push 2 and generate from it this code segment, and so on and so forth. So you see that in order to accomplish this task, you have to be able to generate code in assembly. You have to be able to write code in an assembly language. And so in modules 1 and 2, we're going to do two things. First of all, we'll talk about the virtual machine architecture, abstraction, and commands, the commands of the VM language. And then we're going to talk about actually building this machine by realizing it using a VM translator. And in order to do this, we have to, once again, generate code in assembly. So module 0 is about explaining the notion of low-level programming in assembly language and writing a program or two in order to gain this fundamental competence, without which you will not be able to write your VM translator. Now, in order to do this, we are going to supply you with 9 instruction units, which culminate in what is known as Project 4. And you have to understand that all these units are exact replicas of exactly the same units that we taught in NAND to Tetris Part 1. And in NAND to Tetris Part 1, these units were the substance of Module 4. That's why the project is also called Project 4. And with that in mind, I think that the group of people who are listening to this video now fall into 3 possible categories. First of all, there are people who took NAND to Tetris Part 1, probably recently, and they are happy campers. They enjoy the course, they understand the machine language quite well, and are eager to start working on NAND to Tetris Part 2. Well, if that is the case, we recommend that you review only Unit 8 of the table of contents that you have here, and we highly recommend that you also review your Project 4 in Unit 9. The numbering is a bit confusing here, and you may also consider resubmitting Project 4 if you want. This is an optional project, but just make sure that you remember how to write programs in the HEC assembly language. So that's this group. The second group consists of people who took NAND to Tetris Part 1 in the past, but by now the part of their brains that was committed to machine language is now occupied by some other thoughts. Well, if that is the case, you have to remove the rust, and the best way to do it is to review this subset of units that you see here, and we highly recommend that you do again Project 4 and submit it, but once again, this project is optional in NAND to Tetris Part 2. And finally, there is this group of people who did not take NAND to Tetris Part 1 and decides to jump into NAND to Tetris Part 2 heads-on. Well, there's no need to be gloomy about it. You can certainly do that. But if this is your choice, then we insist that you learn carefully all the units that you see here. And in particular, you must do Project 4. If you will not gain the requisite knowledge of low-level programming, you won't be able to proceed with NAND to Tetris Part 2. So it's up to you to fulfill this prerequisite knowledge. All right, so with that, that's the end of this preliminary unit. Please locate yourself in one of these 3 tracks. In the previous 2 units, we talked about working with registers and memory, branching, variables, iteration, and what remains to be done in order to complete our survey of HEC programming is talk about how we handle something called pointers and how we write programs that manipulate our input and output devices. So that's what we'll do in the current unit. Let us begin with pointers. And as usual, I would like to start with an example in which pointers come to play. In particular, I want you to consider this very simple piece of code that many of you have written in, at least those of you who took programming courses before NAND to Tetris. So in this code segment, I manipulate an array called ARR. I assume that this array has been declared and initialized at some point. And now I write a piece of code that sets the first n entries of this array to the value -1. If you write with a regular high-level language, it's very easy to write such a statement, such a for statement. And as you know by now, when you have to bring it down to the level of machine language, you have to work much harder to deliver the required functionality. So how do we do it? Well, one thing that you have to realize, and in fact you realize it only when you set out to write a compiler, is that the notion of arrays gets lost in the translation, so to speak. So when the assembler has completed to translate this piece of code from, let's say, Java or Python into machine language, the machine language no longer recognizes the array abstraction. And as far as the machine language is concerned, the array is just a segment in memory of which we know the base address of this segment and the length of the array that the programmer has decided to declare. So if we assume that the array starts in address 100 and that we want to do something to the first 10 entries of this array, this is how it's going to look like in the data memory on which this program will end up executing. We start with two variables. One of them holds the base address of the array, and the other one is the number of entries that we want to manipulate. And what we would like to see is that at the end of the execution of this program, we would like to see the first 10 entries of this array set to -1. This is the goal. That's what we want to do. And the question is, of course, how do we actually do it? All right, so let's start working on this on writing this particular program. The beginning of the program is going to set up these variables that we just discussed. So we assign the number 100 to ARR to signify that the array ARR begins in the memory register number 100. And we do something similar with n. We assign the number 10 to n. We initialize I to 0. Once again, don't forget, we're trying to deliver the functionality of a for loop that begins with I equals 0. So we set I to 0, and then we can start actually going through the loop, so to speak. So once we do these three variable declarations and assignments, we have this setting ARR, end, and I allocated to memory registers 16, 17, and 18, and we are ready to begin the actual processing. All right, so here is the actual processing. The first segment of the loop, and by the way, we realize the for loop using a machine language oriented loop, which begins with a label declaration called a loop. And the first thing that we do is we translate the termination condition into machine language. So what used to be if I equals n, go to end, which is the end of the processing, because once I, what is I? I begins with 0 and goes through 1, 2, 3. When it gets to 10 in our example, we want to jump to end. So we have 6 hack instructions that actually perform this semantics. And then we come to the heart of this loop, in which we actually assign the number -1, which is meaningless, by the way. We just use this as an example. We assign -1 to the current entry of the array. How do we do it? Well, let us begin with a comment. As you see, what we are doing is we are computing the value of ARR plus I, which is the value of the base address of this array plus the current value of the index. Now, if the index begins with 0, then the first entry that we're going to operate on is RAM 100, because ARR is 100. And then I will become 1, so we'll operate on RAM 101. And then I becomes 2, we'll operate on RAM 102, and so on and so forth. How do we do it? Well, we have to add up ARR and I, and that's exactly what we do in the first 4 instructions. We say at ARR, we address the variable called ARR. We put the value of this variable in D. Then we say at I, we address the variable I. We add up D plus M, and we put the result in the A register. Now, this is something which is should be new to you, because it's the first time that we actually use this capability of the language to assign something directly to A using an arithmetic operation. Okay. Now, what will happen when we do it? Well, D plus M now store an address. So this address is assigned to A, and by the time we say M equals -1, the register that will be affected is the register that A addresses. Now, if we do this within a loop that runs 10 times or 10,000 times, in each iteration, the A register will acquire one more address, and we're going to operate on a different register in the memory. And that's exactly what we want to do. So after we run so many iterations, we'll get the desired effect. And as usual, we recommend that you stop the video and convince yourself that this is actually working as advertised. So variables that store memory addresses like ARR and I are called pointers in any language, not only in Hack. And in Hack, the typical logic is as follows. Whenever we have to access memory using a pointer, we need some instructions like A equals something that comes from some memory register. So the typical semantics is set the address register to the value of some memory register in which I do some pointer arithmetic to compute the address on which I want to operate. Okay, so this, in a nutshell, is how we do pointer processing in the Hack machine language. In the next part of this unit, in the next and final part of this unit, we will see how pointer manipulation comes to play in the when we write code that interacts with the screen and with other similar peripheral devices. All right, so let's talk about input-output. First of all, if you recall, we have 2 standard input and output devices. We have a display unit and a keyboard, and these I/O devices are connected, so to speak, to 2 designated area in the RAM. One of them is called the screen memory map, and these are 8K of bits that represent about 13,000 pixels on the physical display unit, and we have a keyboard which is connected to yet another area on the memory called which we call keyboard. All right, so we also have these labels that record the base addresses, so we don't really have to remember any actual number when we set out to process the screen and the keyboard. All right, so here's an example of using the screen, and in particular using the screen to draw a rectangle. This is like the hello world of computer graphics, drawing a rectangle. How do we do it? Well, this is a screenshot of our CPU emulator. I want to remind you that what we see here is the ROM, the instruction memory on the left, data memory next to it, and then we see some simulation of a physical screen. We see it at the top right-hand side, and the task in front of us is to draw a filled rectangle at the upper left corner of the screen, and the dimensions of the rectangles are such that it has to be 16 pixels wide and RAM 0 pixels long. So RAM 0 is a parameter of this program, and if you look carefully at the top of the RAM in this slide, you will see that RAM 0 has been set by the user to 50. So once the user puts a number like 50 in RAM 0 and clicks the play icon, what will happen is that the program will start running, and at the end of its execution, which is going to be very quick, you're going to see a rectangle drawn at the top left of the screen. The rectangle is 16 pixels wide. This is a fixed width, and the length is variable according to the input of the user. So this is the mission. That's what we have to do. Before we look at the actual code, let us go into the CPU emulator and actually demonstrate this program working, and then once we do it, we'll talk about the code proper. The purpose of this demo is to illustrate how we can load and execute a program that draws a rectangle at the top left corner of the screen. So what we have here is two windows. In the foreground, I have the CPU emulator, and in the background, I have a plain text editor with the program in question loaded already into it. The program has been written. If we read the documentation, we see that the program claims to want to draw a rectangle at the screen's top left corner, and hopefully that's also what the commands of the program are actually doing. We can scroll through this program and see all sorts of familiar hack commands written in the symbolic hack machine language, along with documentation and white space to make the code more readable and manageable. So let's go to the CPU emulator and click the load program button, which is right here, and look for this program, rectangle ASM. Here it is. Found it, loading it. And it's interesting to contrast the source code with what was actually loaded into the CPU emulator. So let's take this window and put it right next to the loaded code. We see that the source contains all sorts of symbolic addresses like @R0, @N, and so on. Now, all these symbolic addresses are being translated on the fly into their concrete numeric semantics. So if we look at the code that was actually loaded into the CPU emulator, instead of @R0, we see @0, instead of @N, we see @16, and so on and so forth, according to the rules of translation of hack symbolic programs into machine language. This is something that we're going to learn in Unit 6, so please don't worry about it for now. If you want to understand how a program works in the CPU emulator, it's better to look at the source code and not at the code that was actually loaded into the emulator. So you run the program in the emulator, but you inspect and debug it in the text editor, and then you reload the corrected version in order to continue to test it. All right, so let's put this window roughly back where it was before and go back to the CPU emulator. And once again, the program is loaded. We are told that we have to determine the depth or the length of the rectangle by filling in some number in RAM 0. So let's do that. And I'm going to put here the number 50. So we are going to draw a rectangle which is 16 bits or 16 pixels wide and 50 rows long. Hopefully that's what the program is going to do. So I can start executing the program by clicking this play button, and each time I click a play button, I execute the next command in the program. And so far nothing seems to happen, but perhaps we have to be slightly more patient. And indeed, we see that we drew one line of 16 pixels at the top left corner of the screen. Very nice. So let's continue to execute, and looks like there was a loop in the program, and I'm doing it slightly more quicker, and I see that I drew another line and keep on drawing another line, and so on and so forth. If I get tired of this stepwise simulation, I can click the fast forward, and then I can just sit back and watch the program get execute. This is fairly slow, so I can make it faster by using the slider here. And I see now that the program runs much quicker than before, and it keeps on drawing rows until the counter of these rows will reach RAM 0, which now happens to be 50. And that's it. We got this limit. And at that stage, the program executed some goto command that sent it to the end of the program, where it runs an infinite loop. And that's exactly what I want to do at the end of every hack program. So once I get tired of seeing this infinite loop, I can stop the program, look at the screen, and convince myself that the program has actually done what it was supposed to do. Now, let's just scroll back to the top of the program. And we can try some other input, let's say 70. Or let's even make it more a larger number. So we're going to draw a rectangle which is 120 rows long. And if I'm tired to see all this animation, I can click this control here and cancel the animation, at least temporarily. And then I reset the program. And once I've canceled the animation, I can simply click fast forward, sit back, and watch the program execute in an instance. So let's do that. And as you see, a rectangle of 120 rows by 60 pixels has been drawn so-called instantaneously. Of course, as a low-level programmer, you know that this program required 120 iterations, and in each iteration, we had to execute several machine-level commands. So this has been a demo in which we illustrated how to use the CPU emulator in order to execute a graphics-oriented program. All right, so now that we saw that the rectangle drawing program actually works, let's take a look at how we actually do it. And we'll start with pseudocode, because once again, if you get your pseudocode right, it's like 90% of the job done, because the rest of it is translating the pseudocode into machine language, which is a relatively technical thing to do. All right, so let us focus on some. As a programmer, we say that for I go in nicely in I to remember where I am in the loop, and then I'm going to repeat this thing n times. Okay. Now, put your hands on the hardware and program it in a very low level, in a multiplication, multi-purpose device. In this describing. So we expect you to document the program. So if everything worked according to plan, then you have already gone through a machine language primer, and we are ready to move on and talk about what lies ahead. So here's the computer that we built in NAND to Tetris Part 1, and launching NAND to Tetris Part 2 Just like many other classical courses in computer science, we'll start with the familiar Hello World program, which is written here in a language called JEC, a high-level object-based language that we will use in this course, NAND to Tetris Part 2. And so we write this program, we put it into the heck computer somehow, we click something, and boom, the screen displays the words Hello World. Well, in most courses, at this point, students continue to develop some more interesting programs, but in NAND to Tetris, we stop right here and ask ourselves a whole set of interesting questions about what happens below the surface, so to speak. First of all, take a look at this whole notion of program execution, which is nothing short of magic, because after all, the program is just a bunch of dead characters that I wrote on a piece of paper or using some text editor. It's completely static. And all of a sudden, I can take this program and somehow transform it into a set of low-level instructions that cause the computer to actually do something. This is quite fascinating, and we take it for granted. And how did the computer know how to display the words or the images Hello World on the screen? How did it know to display H on the screen? And excuse me, how did it know to display a single pixel on the screen? You know, all these are very interesting questions that we usually don't bother to think about. And what about keywords like class, function, do, while? I mean, we know exactly what we want the computer to do when we write these words, but how does the computer figure out what to do with them? How does it actually even parse our code and understand where these words are located? And even if it understands that it found a while, and that while should supposed to signify a loop, how does the computer know how to execute this loop? And take a look at commands like print screen and print line. It looks like these commands are invoking methods or functions that exist in other classes, right? A class called output, which is presumably not here. It's part of some class library or an operating system. Well, how does the computer know how to pass control to these methods, and then after they do the thing, return control to our program? You know, all these issues and hundreds of similar other questions are extremely interesting and important, and yet high-level programmers don't stop for a minute to think about them. Why are they allowed to act in such a state of bliss of ignorance? Well, the answer is that high-level programmers think about their high.
Ya, esto es interesante porque, o sea, lleva un paralelo con la ciencia, ¿no? O sea, por ejemplo, existen las teorías, pero las teorías son una representación abstracta de la realidad, ¿verdad? Es decir, nunca llegan a ser exactamente la realidad, son solo una abstracción, un punto de vista. De la misma manera, los programas de alto nivel trabajan sobre abstracciones y en un libro de teoría puedes tener lo que significa una clase, tener en tu cabeza que, no sé, es un constructor de objetos y los objetos se relacionan con objetos del mundo real. Y es así como tú programas como un programador de alto nivel, ¿no? Pero en realidad no importa tu abstracción, porque al final lo único que importa es cómo la máquina lo interpreta y ejecuta el código. Al final esa es la realidad, ¿no?
High-level language as an abstraction. And the programs that they write, as far as they're concerned, are also abstractions. Now, being able to hide, excuse me, being able to hide low-level technical details from the users of your system is an extremely important principle, not only in computer science, but in any large-scale scientific or technological project. Because you see, high-level programmers have enough problems of their own. And application programming is a sufficiently interesting and challenging field of work and pleasure. And if we would expect high-level programmers to also think all the time about how to render pixels on the screen and pass the programs and so on, they will go nuts. They will not be able to focus on their own work. So it's actually a virtual.
Claro, y no digo que las abstracciones sean malas, sino que uno debe, al momento de trabajar con abstracciones, también debe tener siempre en cuenta cómo es que se interpreta. No puede, bueno, puedes trabajar solo con la abstracción, pero la, los programas que hagas van a ser, no, no van a tener en cuenta muchas cosas importantes y quizás no sean tan eficientes, o quizás lleguen a la solución, pero no de la mejor manera, ¿no?
That they don't have to think about the low level. However, someone has to think about it. And someone has to, at some point, at least if you know, if you have an inquisitive mind, then you should ask yourself, what makes these abstractions work? And the answer is that what makes them work are things like assembler, virtual machine, compiler, and operating system. And closing this gap, understanding how these things work, is what NAND to Tetris Part 2 is all about. Now, some of you might say, well, I don't understand. Shimon just told me that in order to be an application programmer, I don't have to worry about these things. So why do I have to worry about these things? Well, the answer is that
Ahora, es interesante también pensar qué significa de la mejor manera. Hasta ahora solo entiendo que los programas que haces pensando también en, en cómo lo interpreta la máquina son más eficientes, ¿no? Pero también será posible que sean más fáciles de entender y escribir. Eso es algo que tengo que testear o pensar más.
Indeed, you can write technical details from the users of your system is an extremely important principle, not only in computer science, but in any large-scale scientific or technological project. Because you see, high-level programmers have enough problems of their own. And application programming is a sufficiently interesting and challenging field of work and pleasure. And if we would expect high-level programmers to also think all the time about how to render pixels on the screen and pass the programs and so on, they will go nuts. They will not be able to focus on their own work. So it's actually a virtue that they don't have to think about the low level. However, someone has to think about it. And someone has to, at some point, at least if you have an inquisitive mind, then you should ask yourself, what makes these abstractions work? And the answer is that what makes them work are things like assembler, virtual machine, compiler, and operating system. And closing this gap, understanding how these things work, is what NAND to Tetris Part 2 is all about. Now, some of you might say, well, I don't understand. Shimon just told me that in order to be an application programmer, I don't have to worry about these things. So why do I have to worry about these things? Well, the answer is that indeed, you can write very nice high-level programs without understanding compilers and operating systems internals. And yet, if you do so, you will be stuck in a certain limited and constrained level of competence. However, if you will take the time to indulge yourself in understanding how these wonderful software layers work, you will become a far more competent and sophisticated software developer. And not only that, you will also become a much richer person, intellectually speaking. Because in order to develop a VM, a compiler, and operating system, you have to learn how to use some incredibly beautiful algorithms, data structures, programming techniques, and all sorts of things that will advance you tremendously, not necessarily in understanding the low-level details, but in general, as a software developer and as a thinker. And also, of course, as an applied computer scientist. All right, so with that in mind, here's the big picture. These are the major stations in our journey. And the last station is a high-level language. And I would like to devote this unit to discussing the end of our journey. Now, what will happen at the end? Well, at the end, we'll be able to write programs in the Jack language, which is quite similar to Java in many respects. And I would like to give you an example of how these programs will look like. So I've chosen arbitrarily a little problem in playing with points in a two-dimensional space. So what we see here are the points P1 and P2. And the point P3 is the vector addition of P1 and P2. And it looks like we're interested in the distance between P1 and P3. How can we perform such manipulations using Jack? Well, it turns out that someone has already written a class called point that includes various services which are quite useful in order to carry out such 2D manipulations. And this person gave me not only the class, he or she also gave me the API to this class. So I can use this API to write a little program that performs what you see here on the picture. And here's the program. So I open my text editor and I write these lines of code. I define a new class. I call it main, a new function, which is also called main. And then I declare three object variables called P1, P2, and P3. The type of these variables is point. And then I go on to construct P1 and P2. I know how to do it because I have the API. So I read the constructor signature, and based on this, I initialize and construct these 2 points and assign them to the object variables P1 and P2. And then I have to add up P1 and P2. I look at the API. There is a plus method, so I use it according to its signature. I get to construct a new point, P3. And then for debugging purposes, I print this point on the screen. If this program were running now, which it doesn't yet, but if it were running, I would see hopefully 46 on the screen. And then I print line and compute the distance, the Cartesian distance between P1 and P3, and I print it. I do it in the same statement. And once again, if this were executed, I would see hopefully the number 5, and then I return. All right. So I used the point class as an abstraction and did some manipulations that did exactly what I wanted to do. And I think that this little example here shows you the tremendous power of object-based programming, because with something like 10 lines of code. I used my Cartesian distance running now, P3. And then for debugging purposes, I print this point on the screen. If this program were running now, which it doesn't yet, but if it were running, I would see hopefully 46 on the screen. And then I print line and compute the distance, the Cartesian distance between P1 and P3, and I print it. I do it in the same statement. And once again, if this were executed, I would see hopefully the number 5, and then I return. All right. So I used the point class as an abstraction and did some manipulations that did exactly what I wanted to do. And I think that this little example here shows you the tremendous power of object-based programming, because with something like 10 lines of code, I managed to do some very useful work, provided, of course, that someone took the trouble to develop the point class for me. So indeed, what I'd like to do next is delve into the point class, and let's do it. So the first thing that we do when we open up the implementation of point is that we see that we have some class-level declarations. So the class begins by declaring that x and y are, or let me put it otherwise, it begins by declaring that every object of type point is characterized by 2 numbers, x and y, which are the coordinates of this point. And then there's a class-level static variable called point count that stores how many point objects were designed or constructed so far. And now comes the constructor. The signature is the same as we had in the API, and here's the body of the constructor. There's nothing mysterious here. It looks very similar to Java or Python if you are used to these languages. And the only difference, I guess, is that the constructor ends with an explicit return statement, which is implicit in languages like Java and Python. And in this explicit statement, it returns the address of the object that it just created, and this address goes right into P1 and P2 in the caller's code, so everything works as expected. And let's continue to pursue this class. So this is what we've seen before. There are some accessors that I didn't bother to list in the API. Here's the definition of the plus method, and you can look at the algebra later if you want and convince yourself that it indeed carries out vector addition. And let's see, we also have this Cartesian distance method, which uses the Pythagorean theorem. And I think, and then we have the print method, and that's it. Now, there's an important point I'd like to make, so please look at me and not at the code. The point is that there's no point really in trying to get too much into the point class, because the purpose of this unit is not to teach you Jack, and neither is it to teach you object-based programming. The purpose is just to give you a flavor of what object-based programming in Jack is all about, and just to give you the feeling that it looks very similar to what you probably did in other programming languages in other introductory to computer science courses. So Jack is quite a simple and sort of plain vanilla language for those of you who have some experience in programming. All right, so to recap, what we had here is two classes, main.jack interacting with point.jack in order to carry out some manipulations. And to remind you, we are now located at the last station of our journey. And what I'd like to pursue next is the question of how do we take this high-level code and bring it all the way down to executable code that can actually run on our bare-bone hardware. Well, here's how we do it. We take these two classes, main and point, and we put them in some directory on our computer, and we call it any name we want. I decided to call it a directory on our computer, and we call it any name we want. I decided to call it points in there, run on our bare-bone hardware. Well, here's how we do it. We take these two classes, main and point, and we put them in some directory on our computer, and we call it any name we want. I decided to call it points in the plural. Then we apply the Jack compiler to this entire directory, and as a result, we will get two new files that have the same prefix names, the same class names, but a VM extension instead of a Jack extension. And these two files will be in the same directory as our source code. And by the way, if you're used to Java, this is exactly what you do with Java, right? Because you start with, in Java, it will be two Java classes that have a Java extension instead of a Jack extension. And after you apply Javac, the Java compiler, you will get two classes written in bytecode, and the extension will be class instead of a VM, just a small syntactic detail. And then you probably don't know it, but you're going to apply something called the VM translator, which in Java is done using the command Java itself. And in our world, the VM translator is going to translate the VM code into one file that contains many instructions in heck assembly. Then we can take this ASM file, as you see here, and give it to the assembler. The assembler will finally produce from it another file with a heck extension, and then we can take this file, put it into the computer that we built in Untitled Chapter Part 1, run it, and voila, we're going to see the output of our program flickering on the screen in front of us. So that's the process of taking a high-level program and moving it through the hoops until it gets into something that can be actually executed. And during Untitled Chapter Part 2, not only we will do these things many times, we'll actually build all these tools ourselves. All right, so once again, here's the course plan. We start with module 0, in which we ask you to get acquainted with heck assembly. Very important to do it. And once we do this, we move on to the next two modules, in which we will build a virtual machine and a VM translator. And then we'll jump to the end of the journey, and we'll ask you to write some non-trivial program in Jack. Obviously, we'll teach you a lot about how to use the Jack language. Not too much, because Jack is self-explanatory. But then we will use this language in order to develop some interactive game or some other simple program. And then once you understand the language itself, once you get familiar with the language itself, we'll write a compiler for this language, for Jack. We'll write a compiler using something like Java or Python, a language that you feel comfortable with. And then finally, in the last module of the course, we'll develop the operating system that provides all sorts of important extensions to Jack, and that closes all sorts of gaps between high-level programming and the bare-bone hardware. So before we take off in our Nanto Tetris Part 2 journey, I'd like to say some words of disclaimer and run a little self-inspection together with you. So first of all, I want you to know that Nanto Tetris Part 2 is much more demanding than Nanto Tetris Part 1. I think it's just as much fun as Part 1, but you will have to write many programs and do lots of projects. So you have to make the proper, I think, mental and time commitment to take a rigorous and challenging course, although it's going to be a lot of fun, and I think that you're going to enjoy it tremendously. But still, there's going to be a lot of work. Now, during this unit that we just went through, I showed you several examples of high-level programming using the Jack language. And I want to ask you the following question, and please, I want you to answer it sincerely in your heart of hearts, so to speak. Are you comfortable seeing these programming examples? Do you feel comfortable with things like objects and constructors and reference variables and applying a new operation in languages like Java or C#? If the answer is yes, if you understand what the classes, methods, and constructors are and so on, then you're ready to take this course. If the answer is no, then I beg that you don't take the course and instead go and take some Introduction to Computer Science course, learn the ins and outs and of high-level programming using some decent object-based language like Java or Python, and only then come back to us and complete Nanto Tetris Part 2. Of course, you can enjoy the lectures, or at least some of them, I hope, without doing any projects, but then this will miss the purpose of this course. So once again, if you feel comfortable, fine. If not, you should need some preparation. So if the answer is yes, then I hope without doing any projects, using some decent object-based challenging course, or then come back.
Hola, hola. Bueno, chicos, ayer
To us and complete NAND to Tetris Part 2. Of course, you can course and instead go and take some introduction to computer science course, learn the ins and outs and of high-level programming using some decent object-based language like Java or Python, and only then come back to us and complete NAND to Tetris Part 2. Of course, you can enjoy the lectures, or at least some of them, I hope, without doing any projects, but then this will miss the purpose of this course. So once again, if you feel comfortable, fine. If not, you should need some preparation. So if the answer is yes, then my next question is, we also saw quite a few examples of low-level programming throughout this unit. So my question to you is, do you feel comfortable with low-level programming using the heck assembly language? Do you understand what A equals M is? What is A? What is M? What is the meaning of this operation? If the answer is no, then I request that you go back to the machine language primer, learn what you need from there according to my guidelines, and do project 4. Do this project, assign it or submit it, get a grade on it, and then come back to continue to work on NAND to Tetris Part 2. If the answer to both questions is a resounding yes, then welcome aboard. You're ready to take NAND to Tetris Part 2, and we can move ahead and actually start the course. And in the next unit, we're going to talk about some compilation aspects, and then we'll start to actually build our virtual machine. Welcome to Unit 1.1 in our virtual machine module. Here again is the big picture. And we already know how to deal with the hardware. We know how to write programs in the heck assembly language, and we're ready to move on. And actually, we are now beginning the process of writing a compiler for a modern object-based language. And because this is quite a substantial task, we will divide it into quite a few modules, beginning with this module, Module 1. And because in this course we do everything bottom up, we'll start on the right-hand side of this roadmap here, and we'll begin writing our VM translator. But before we actually get into all these nitty-gritty details of building the virtual machine, I think that it makes sense to actually take a look or have a sneak preview at the end of our journey and talk about the overall task of compiling a high-level language. So let us once again review the code that we saw before in the previous unit, in which we manipulate some points in a two-dimensional space. And I wish to remind you that if you run this code on a computer, then you'll end up seeing some output flickering on the screen. No, this is not just a bunch of characters. These are points that were derived using vector algebra and the Pythagorean theorem and so on and so forth. So indeed, it's kind of staggering how we accomplished that, how we started with this abstract program on the left and ended up with something that actually runs on the computer. How can we make it happen? Well, first of all, you need a computer. So if you took NAND to Tetris Part 1, you built such a computer. But even if you had such a computer, you would still need to translate all the way from high level to the machine language of that computer. And that's what NAND to Tetris Part 2 is all about. So how do we do it? Well, you know the answer. We need a compiler. We need to translate from Jack, in this case, to the heck machine language or to any other machine language that comes to your mind. So we need to write this compiler. So already now we have a major problem. And the problem is that the world consists of many different computers. So if you start with some high-level program, you would like your program to run on many different platforms, on laptops, desktops, tablets, smartphones, digital watches, and so on. And the problem is that many of these devices use different processors, and these different processors have different machine languages. So it's not enough to write one compiler only. You have to develop many compilers, one for every different processor. And if you're practicing software developers, you have to translate your program to many different target platforms. You have to maintain multiple versions of your code, which is a major pain. So I'm pleased to tell you that there's an alternative. And the battle cry of this alternative is write once, run anywhere, as opposed to write once and fix everywhere. And the best example of this approach is probably Java. Now, Java does not compile all the way down to machine language. Instead, Java employs something called
ya. Aquí quiero notar que las abstracciones en los programas son a su vez una abstracción del mundo real. Y por ende, por ejemplo, si uno ve en un programa teorema de Pitágoras, este opera bajo números que están representados por bits. En el teorema original matemático son números abstractos y que pueden tener infinitos decimales, pero en la realidad en la computadora tiene una cantidad limitada de bits, por lo que ¿será exactamente el teorema de Pitágoras o es una versión simplificada del mismo? Me parece que sí, ¿no?
called two-tier compilation. So in the first tier, we can call it the top tier, the Java compiler translates the Java program into something called, in the world of Java, it's called bytecode, but in general we call it VM code. Now this VM code is designed to run on an abstract, we can call it the top tier, the Java compiler translates the Java program in, and the best example is something called two-tier compilation. So in the first tier, we can call it the top tier, the Java compiler translates the Java program into something called, in the world of Java, it's called bytecode, but in general we call it VM code. Now this VM code is designed to run on an abstract artifact called a virtual machine. It's not a real computer, it's an imaginary computer. So if we want to actually execute this bytecode, translates the Java program into something called, in the world of Java, it's called bytecode, but in general we call it VM code. Now this VM code is designed to run on an abstract artifact called a virtual machine. It's not a real computer, it's an imaginary computer. So if we want to actually execute this bytecode, we have to translate it further into machine language. We have to realize it on some real von Neumann machine or some real hardware device. So in order to do this, we need the tier 2, the second tier or the bottom tier of the compilation process, in which we equip the target device with something called Jvm implementation in the world of Java, the Java machine implementation. And the Jvm implementation is a program that takes bytecode and translates it finally into the target code of the target platform. And we need such a translator for every platform on which we want to execute our VM program. And you see, the translation gap between the high level and the low level is huge. And by introducing an intermediate level, we are decoupling this very complex process into two separate standalone sub processes, the compiler and the VM translator, or the VM implementation. And every one of these translators is significantly simpler than the compiler that we saw before, that goes all the way from top to bottom, like, for example, C++. So we have broken a very complex task into two simpler tasks, which is always desirable. And in fact, Java should not take credit for this idea of two-tier compilation, because the idea is about, and the practice is about 30 years old. And in fact, if you think about it, it's almost, believe it or not, it's almost 90 years old, as I will comment later on toward the end of this module. So how do we do it in Jack? Well, Jack is a Java-like language, which we use in this course, and we are going to execute Jack programs on two different platforms. One platform will be your own PC, whatever PC you're using, and the other platform is going to be the hack hardware that we built in part 1 of Nanto Tetris. If you didn't take Nanto Tetris part 1, don't worry about it. You don't need the actual hack computer, because the Nanto Tetris software suite, which is now sitting on your computer, includes an emulator that simulates the hack computer on your PC. So you can do everything that has to be done in this course using this simulator. So how do we bridge the gap between Jack and these two target platforms? Well, we do something very similar to what we did with Java. We will write a compiler that compiles Jack programs into what we call VM code, and then we'll equip your PC with something called Jvm Emulator, which is a piece of software that knows how to take a VM program and actually execute it on your own laptop or whatever machine you're using. At the same time, and parallel to this approach, we will also write a substantial program, a VM translator, that takes the VM code and translates it into the machine language of the hack platform. And this emulates the hack computer on your PC. Don't worry about it. You don't need Jack programs on, believe it or not, it's almost 90 years old, as I will comment later on toward the end of this module. So how do we do it in Jack? Well, Jack is a Java-like language, which we use in this course, and we are going to execute Jack programs on two different platforms. One platform will be your own PC, whatever PC you're using, and the other platform is going to be the hack hardware that we built in part 1 of Nanto Tetris. If you didn't take Nanto Tetris part 1, don't worry about it. You don't need the actual hack computer, because the Nanto Tetris software suite, which is now sitting on your computer, includes an emulator that simulates the hack computer on your PC. So you can do everything that has to be done in this course using this simulator. So how do we bridge the gap between Jack and these two target platforms? Well, we do something very similar to what we did with Java. We will write a compiler that compiles Jack programs into what we call VM code, and then we'll equip your PC with something called Jvm Emulator, which is a piece of software that knows how to take a VM program and actually execute it on your own laptop or whatever machine you're using. At the same time, and parallel to this approach, we will also write a substantial program, a VM translator, that takes the VM code and translates it into the machine language of the hack platform. And this actually will be sort of the pinnacle of module 1, of what we do in this particular module. But it will take us several units to get to this level, several units of instruction. So to sum up, in this module, in the next one, we are going to write the VM translator. We're going to first of all understand what is a virtual machine, and then we're going to implement it. And then in modules 4 and 5, we're going to write the compiler that will complete the overall compilation picture. Now, I wish to remind you that the virtual machine is an abstraction. It's an imaginary artifact, and it's an example of what we call virtualization, which is one of the most important ideas in the theory and practice of computer science. And you cannot do cloud computing and communication networks and modern programming languages without using this notion of virtualization in a major way. Now, I can think about one person who will be delighted to see what we're doing here, and this is Alan Turing, one of the most distinguished granddaddies, if not the most distinguished grandfather of the computer science field. Almost 90 years ago, Turing wrote a seminal paper in which he described an abstract computer that had the ability to basically execute computer programs abstractly. And he also described something called universal machine, now it's called universal Turing machine, that can take any other machine and emulate its operations. And by doing this, by thinking about a machine that executes another machine, or a program that executes and understands another program, a program that treats another program as data, by doing this, Turing really put computer science on a completely new level of sophistication. Because you see, this notion of thinking about thinking, this is a hallmark of intelligence in general. What's the difference between you and your dog? Both of you are thinking creatures, but you can think about thinking. And I'm not sure that your dog can perform this trick. So in computer science, we can write programs that analyze other programs, run other programs, manage them in all sorts of different ways. And this ability to sort of reason about reasoning is what makes computer science such a sophisticated and powerful field. Now, we don't have too much time to talk about it because this is a different course. And with that in mind, I'm reminded of some very nice quote that Turing said, and that is, we can only see a short distance ahead, but we can see plenty here that needs to be done. And I think this is a very good slogan for this course. And with that, I want to remind you that this is our overall map. We have plenty of work to do. So enough talking about thinking, and let's build some computers. So in this module, we are going to focus on the virtual machine, and we're going to do it in using two separate perspectives. First, we'll think about what the machine can do for us.
Entonces este es el paso de fabricar relojes a fabricar un programa que represente un reloj, ¿no?
For us, this is the abstract view of the machine, and then we'll talk about how to actually build it. So enough talking about thinking, and let's build some computers. So and I'm not sure that your dog can perform this trick. So in computer, another program is data. By doing this, see what we're doing here, and this is Alan Turing, one of the most distinguished granddaddies, if not the most distinguished grandfather of the computer science field. Almost 90 years ago, Turing wrote a seminal paper in which he described an abstract computer that had the ability to basically execute computer programs abstractly. And he also described something called universal machine, now it's called universal Turing machine, that can take any other machine and emulate its operations. And by doing this, by thinking about a machine that executes another machine, or a program that executes and understands another program, a program that treats another program as data, by doing this, Turing really put computer science on a completely new level of sophistication. Because you see this notion of thinking about thinking, this is a hallmark of intelligence in general. What's the difference between you and your dog? Both of you are thinking creatures, but you can think about thinking. And I'm not sure that your dog can perform this trick. So in computer science, we can write programs that analyze other programs, run other programs, manage them in all sorts of different ways. And this ability to sort of reason about reasoning is what makes computer science such a sophisticated and powerful field. Now, we don't have too much time to talk about it because this is a different course. And with that in mind, I'm reminded of some very nice quote that Turing said, and that is, we can only see a short distance ahead, but we can see plenty here that needs to be done. And I think this is a very good slogan for this course. And with that, I want to remind you that this is our overall map. We have plenty of work to do. So enough talking about thinking, and let's build some computers. So in this module, we are going to focus on the virtual machine, and we're going to do it in using two separate perspectives. First, we'll think about what the machine can do for us. This is the abstract view of the machine. And then we'll talk about how to actually build it, how to implement it, and make it work. This module is going to introduce lots of goodies. First of all, we're going to talk about compilation, as we have done already. We're going to understand virtualization in a very intuitive and deep way. We'll talk a lot about the VM abstraction, and by doing this, you will understand how the JVM of Java works and how the virtual machine of C# works, and so on. We will learn how to use stacks, which is a very important data structure in the theory and practice of computer science. We will actually build the virtual machine, we'll implement it, and in doing so, we'll use pointers, and we'll also do a good share of programming. So a lot of fun is coming up. Bear with me, and let's move on to the next unit. In the second unit of this module, we'll begin exploring the VM abstraction, and we'll start by talking about the most important element in the abstract VM architecture, which is the stack. Now, I wish to start with the big picture, as usual, and remind you that we are developing a two-tier compilation process. And the centerpiece of this process is the virtual machine that operates the VM code that you see here in the center of this slide. Now, let us assume that we had a complete freedom of designing this VM language that sort of sits in the middle of this translation process. How would we go about designing it? Which language would we come up with? Well, we have to strike a balance between two conflicting objectives. On the one hand, we want the VM language to be sufficiently high, you see here in the center of this slide. Now, let us assume that we had a complete freedom of designing this VM language that sort of sits in the middle of this translation process. How would we go about designing it? Which language would we come up with? Well, we have to...
I think, creo que es fácil, ¿no? Solo necesitas una relación de 1 a 1 con los machine instructions. Obviamente cada target va a tener una machine instruction diferente, pero al final representan lo mismo. Así que debería haber un solo símbolo para cualquiera de los dos. Obviamente es una sola dirección. Bueno, no en realidad, ¿no? Pero en este caso es una sola dirección.
To strike a balance between two conflicting objectives. On the one hand, we want the VM language to be sufficiently high so that the distance, so to speak, between the high level and the VM level will be relatively low. And therefore, the translation challenge will be relatively manageable, and the resulting VM compiler will be a relatively simple and elegant program. On the other hand, we want the VM code and the VM language to be sufficiently low so that the distance that we have to cover between it and the final target language, the low-level language, will also be manageable and conveniently small, so that the VM translator or the VM implementation will also be a relatively simple and elegant program. So, we have to find the right balance. And years of research and practice in computer science have indicated that one architecture that hits a very good balance between these two objectives is something called stack machine. And the stack machine is an abstraction that consists of an architecture, a stack, and a set of operations which we can apply to this architecture and an elegant program. So, we have to find the right balance. And years of research and practice in computer science have indicated that one architecture that hits a very good balance between these two objectives is something called stack machine. And the stack machine is an abstraction that consists of an architecture, a stack, and a set of operations which we can apply to this architecture. And this is a good summary of what we're going to do from now on. We're going to describe this architecture and this set of commands. So let's begin with the stack. One way to think about stacks is to envision a stack of plates that has a top, of course, and to come up with some sort of a game in which we have only two allowable manipulations. One of them is called push for historical reasons, and this operation allows us to put a plate on the top of the stack, and pop allows us to remove the top plate from the stack. And as we do these operations, the top pointer moves accordingly to reflect what we have just done. And the top pointer always points to sort of one position above the topmost plate in the stack. Now, with a regular stack of plates, you can take a few plates, take them up and put another plate in the middle. But in this stack, you're not allowed to do it. You can only access the stack from the top. Now, in computer science, stacks look somewhat different, but the idea is exactly the same. The stack contains some values instead of plates, and these values, we can think about them as integers, but in general, these integers can represent anything. They can be strings, they can be Boolean values, and so on. But let's think about integers to make life simple. And we have something called a stack pointer that points to the location in which the next value is going to be pushed. This stack is available in a larger context called the virtual machine, which is also equipped with a regular sort of memory segment, which is very similar to the RAM that we built in part 1 of the course. And you can basically think about it as an array which is very similar to the RAM called in which the next value is going to be pushed. Points to the location in which the next value is going to be pushed, just to make life simple. And we have something called a stack pointer that points to the location in which the next value is going to be pushed. This stack is available in a larger context called the virtual machine, which is also equipped with a regular sort of memory segment, which is very similar to the RAM that we built in part 1 of the course. And you can basically think about it as an array which offers direct access to every element in this memory space, as opposed to the stack, which offers only access through the stack pointer. Now, what can we do with this architecture? Well, suppose we do push X. And by the way, we assume that we can label different locations in the RAM as we please. So if we do push X, well, let's check X contains the number 7, and therefore we see the number 7 being added to the top of the stack, and nothing happens to the memory. Okay, another thing that we can do is pop Y, which will affect two separate sort of sub-operations. One sub-operation will remove the top value from the stack, this 3, and the second operation will take this value 3 and store it in location Y. So whatever used to be location Y is going to be overridden. So these are the two fundamental operations that we're going to use in order to move data from the stack to the memory and vice versa. Now, in addition to this, we're going to have a whole set of arithmetic commands. For example, if we say add, the following thing is going to happen. We're going to pop the two topmost values from the stack. We're going to add them up on the side, so to speak, and then we're going to push the result onto the stack. So the result will be this. Notice that the operands of the addition of the stack. So the sides, two things going to. Now, in addition to this, we're going to have a whole set of arithmetic commands. For example, if we say add, the following thing is going to happen. We're going to pop the two topmost values from the stack. We're going to add them up on the side, so to speak, and then we're going to push the result onto the stack. So the result will be this. Notice that the operands of the addition, in this case 3 and 7, have been replaced by the result of the addition, in this case 10. We can do something similar with another addition, in this case, so the side, so to speak, most values. For example, if we say add, the following thing is going to happen. We're going to pop the two topmost values from the stack. We're going to add them up on the side, so to speak, and then we're going to push the result onto the stack. So the result will be this. Notice that the operands of the addition, in this case 3 and 7, have been replaced by the result of the addition, in this case 10. We can do something similar with another command called neg, which will negate the topmost value. Now, it will not simply negate it. It will, first of all, pop the top value. It will negate it on the side, and then it will push the result back onto the stack. So in general, if you want to apply a certain function on the stack, you have to do three different things. First of all, you have to pop from the stack as many operands as are necessary. Then you compute the function of these operands in a separate process, and then you push the result back onto the stack. Now, I said you, but all these things happen, quote unquote, automatically. It's part of the abstraction. So the abstraction supports all these operations inherently. You don't have to worry about them. All you have to do is say add, neg, and these things will take place. Now, in a similar fashion, we can also apply all sorts of Boolean operations on the stack. So in this example, if we say ik, we're going to implicitly pop the two top values, which happen to be equal. We're going to ask, are they equal? Is it true that 5 equals 5? The answer is yes, so we're going to push true to the stack. Then we can say, if we want, we can say or. We will pop the two topmost values. The stack will become empty. We'll or them on the side. We'll get true, and then we'll push true back onto the stack. So I hope that you understand sort of the spirit of this very elegant virtual machine. Now, at this point, you may well ask yourself, where do these commands come from? Push, pop, add, neg, ik, or. Who gives us these commands? What's the story here? Now, actually, I'm not obliged to answer this question. And I can so-called ask you to forget about the outside world and just focus on the VM abstraction, which is a sufficiently attractive, elegant, and powerful architecture in its own right. Okay, it's a good abstraction in its own right, and we may well dwell on it without worrying on what exists outside this abstraction. And you have to understand that there's a certain virtue to this bliss of ignorance, because we can focus on what we're doing now in sort of 100% level. And that's how some great minds really think. They're able to isolate themselves from anything else and just focus on what they're currently working on. But in this course, people who take this course, people like you, are intelligent students who take this course because they want to understand the big picture. So it's in the DNA of this course to ask questions like, where does this come from? Where are we going from here? And so on and so forth. So I allow myself to actually venture outside the context of the virtual machine and say a few words about the big picture of stack arithmetic. Where do these commands come from? Well, they come from the compiler that we haven't seen yet. Okay? So if you start with a high-level statement like x equals 7 plus 19, the compiler that we will build later on in the course is going to translate it into, in this case, push 17, push 19, add, and pop x. Okay? And the result of executing all these operations will put in x the value of 17 plus 19. Now, there's an interesting abstraction implementation interplay going on here. First of all, the high-level language, of course, is an abstraction. It doesn't exist for real. It can be implemented by translating it into code that operates on a stack machine. But the stack machine is also an abstraction. But the stack machine into code that operates on a stack machine. But the stack machine is also an abstraction. And this abstraction is implemented by something else. Stay tuned, because the whole gist of this module is to understand this abstraction and implement it, as we'll do later on in the module. All right, so here is the virtual machine in its whole glory. It's a stack machine which is manipulated by 4 categories of commands: arithmetic logical commands, memory segment commands, branching commands, and function commands. And what we'll do next is talk a little bit more about arithmetic and logical commands. So here's an example. We start with this high-level code, which the compiler is going to translate into this VM code. How this translation takes place is something that you shouldn't worry about at this stage of the course, because we'll worry about it later on in about 2 or 3 modules from here. Now, we do want to worry about how to execute this code, because this is squarely within the VM abstraction. So here's an empty stack to begin with, and we assume that we have a memory segment with x and y variables, and then we say push 2, so the stack becomes 2, and then we push x, so the value of x is being pushed onto the stack. We subtract these 2 values, we get the result. We then push y, the stack grows. We then push 9, the stack continues to grow. We then add up the 2 topmost values, and we get, I think, 21. Then we do another addition, and we get -4 plus 21, which gives us 16. And finally, we pop the result into D, and we get a new variable D, which contains the value of this computation. So what we saw here is a typical sequence of stack machine commands executing and achieving some useful value. Now, we could have done something very similar with logical commands. And here's an example. What we see at the top of this code pane here is a logical expression, or Boolean expression that has a truth value. And in order to evaluate this expression, the compiler will generate this code, the code that you see here. So starting again with an empty stack and some x and y assumptions, we can execute every one of these commands one after the other. And what we'll end up getting is this simulation that you see here. And if you want, maybe you can stop the video here, go through the motions, and convince yourself that you understand what is going on here from one transformation to another. So please do this. So to recap what we've done so far, here are our arithmetic logical commands. We have 3 arithmetic commands, add, subtract, and negate, that always operate on the topmost values in the stack. Then we have 3 logical comparisons command, equal, greater than, less than, which also operate on the 2 topmost values in the stack. And finally, we have the 3 classical logical connectors, and, or, and not, that also operate on the 2 topmost values of the stack. Now, this doesn't look like much, right? It looks like a very sort of a Spartan set of commands. But here's an interesting observation. Any arithmetic and logical operation that you can dream of, written in any programming language, can always be reduced to a subset of operations that uses these commands and executes them on a stack machine. And the stack machine will end up computing the value that you wanted to compute in the high level. So this goes on to show the underlying power of this very simple virtual machine that we're building here. All right, so with that, here's once again a description of the overall VM language. We have said everything that we want to say about the arithmetic and logical commands, and in the next module, we'll talk about memory segment commands. In this unit, we're going to talk about memory segments and memory segment commands. So here, once again, is our overall VM language that consists of 4 categories of commands. We already explored the arithmetic logical commands in the previous unit, and now we're going to move on to memory segment commands. Now, let's start with the big picture. We have this arbitrary example of a high-level piece of code, and we want to translate it or compile it into VM code, something that we'll worry about later on in the course. Now, let's focus on this statement as an example. Let c equals s1 plus y. The compiler will generate or will translate it into push s1, push y, add, and pop c. And once again, how the compiler does it is something that we'll worry about later. Now, I want you to notice that something kind of gets lost in the translation. If we look at the high level, we know from our experience and from our knowledge of the high-level syntax of this language is that different variables have different roles, right? S, for example, or S1 is a static variable, and C happens to be, let's see, C happens to be a local variable, and Y is an argument. So these different roles of the variables is something that we also want to preserve, of course, in the virtual machine abstraction. If we won't preserve it, things will go wrong in the execution of this program. So we need some mechanism to record the different roles of different variables in one's program. And we do this by introducing the notion of memory segments, which is part of our VM abstraction. So our stack machine is going to be equipped not with a single memory segment, as we had so far, but rather with several memory segments with names like argument, local, static, and a few more, as you'll see later on. Once we have these segments in place, the compiler can map the variables of the high level on these segments. And in this particular example, we'll get this particular mapping. And once we have this mapping in place, we can use it in order to generate code. So instead of push S1, let's see, S1 is a static variable. So instead of saying push S1, we're going to say push static 0. And instead of pushing Y, which is argument number 1, we're going to say push argument 1. And instead of saying add, well, add is add. There's nothing to add. But instead of saying pop C, we're going to say pop local 2. So we see that once we use the segments in this way, we're going to be able to preserve the role semantics of these variables also in the VM abstraction. But something interesting has happened. We lost the variable names in the process. And indeed, the VM abstraction does not recognize symbolic variable names. All variables are replaced by references to memory segments, as we see here. And this is not something which is unique to our VM. Our VM, by the way, is modeled after the Jvm, the Java Virtual Machine, in broad terms. And the Jvm also does not have symbolic variables. It only has references to symbolic memory segments. So as you see, we have extended the story. And instead of interacting with a single memory stream, we now interact with several different memory segments, to which we also add a segment that we call constant, which is truly a virtual segment because it contains just the numbers 0, 1, 2, and so on and so forth. And once you have these segments in place, well, the commands that you're going to use, the push and pop, are going to take as arguments the name of the segment that you want to operate on and the index in that segment. So here are some examples: push constant 17, push local, pop local 2, pop static 5, and so on and so forth. Now you may ask yourself, why do we need push constant 17? Why can't we just say push 17? Well, we think that it's nicer that it's nice that all the VM commands, all the push pop commands will have the same syntax, a consistent syntax, and this is a very small price to pay for this consistency. It also makes compilation easier. Small price to pay will have the same syntax, a consistent syntax. Well, we think that it's nicer that constant the index in that segment. So here are some examples: push constant 17, push local, pop local 2, pop static 5, and so on and so forth. Now you may ask yourself, why do we need push constant 17? Why can't we just say push 17? Well, we think that it's nicer that it's nice that all the VM commands, all the push pop commands will have the same syntax, a consistent syntax, and this is a very small price to pay for this consistency. It also makes compilation easier, as we'll see down the road. All right, so in order to make life interesting, we actually have not 4 but 8 virtual memory segments. Why do we need so many segments with names like local, argument, this, that, constant, static, pointer, and temp? Well, let us not forget where we're coming from. We're coming from the world of a high-level object-oriented language. And there's a lot going on in high-level object-oriented programming, right? There are static variables, local variables, argument variables. There's the current object that a method is processing, and this object is also a bundle of variables. There's an array that the method can process, and so on and so forth. So there's lots of semantics going on. And in our virtual machine, we can handle all the semantics using the 8 virtual segments that you see here. Now, the good news is that all these segments behave exactly the same way once we are within the VM abstraction. You push a value into a memory segment by saying push memory segment name and index. And so segment can be any one of these 8 segment names, and I is simply a non-negative constant. What about pop? Well, it's almost the same, with the exception that you cannot pop into the constant segment because it simply doesn't make any sense. All right, so these are the push and pop commands, 8-segment instruction. You push a value that is also a bundle of argument, this, that, constant, static, pointer, and taxi down the road. All right, so in order to make life interesting, we actually have not 4, but 8 virtual memory segments. Why do we need so many segments with names like local, argument, this, that, constant, static, pointer, and temp? Well, let us not forget where we're coming from. We are coming from the world of a high-level object-oriented language. And there's a lot going on in high-level object-oriented programming, right? There are static variables, local variables, argument variables. There's the current object that a method is processing, and this object is also a bundle of variables. There's an array that the method can process, and so on and so forth. So there's lots of semantics going on, and in our virtual machine, we can handle all the semantics using the 8 virtual segments that you see here. Now, the good news is that all these segments behave exactly the same way once we are within the VM abstraction. You push a value into a memory segment by saying push memory segment name and index. And so segment can be any one of these 8 segment names, and I is simply a non-negative constant. What about pop? Well, it's almost the same, with the exception that you cannot pop into the constant segment. Because it simply doesn't make any sense. All right, so these are the push and pop commands operating on the memory segments. So here's a little quiz for you to practice what we've learned so far about memory segments. This is just a typical sort of state of a virtual machine with several memory segments present, with some values in them and some values in the stack. And let us assume that we want to carry out the pseudo operation static2 equals argument 1. Now, we cannot do something like this in the syntax in the Vim language. We have to use the available commands that we learned so far. Now, static2 happens to be argument 1 happens to be 12. So at the end of the game, we want to see this particular machine state, which is identical to the previous one, except that static2 now contains the value equal to this particular machine state, which is identical to the previous one, except that the argument 1 happens to be 12. So at the end of the game, we want to see this particular machine state, which is identical to the previous one, except that static2 now contains the value 12. So the question is, which VM commands will make this magic happen? So why don't you think about it for a minute or two, write down commands, and then continue to run the video, and you will see the answer. So here's the answer. In order to move the value of argument 1 to static2, we must go through the stack. That's the only way to do it in a stack machine. So we push argument 1 onto the stack, and then we pop the topmost value, the value that we've just added, onto static2. And because these two commands kind of cancel each other stack-wise, we see that the stack remains the same. A lot of drama happened, right? We added something, we took something away from the stack, but at the end of the game, the stack is intact. And we managed to move something from one segment to the other, and that's the only way to move values from one segment to another in our VM abstraction. So to recap, here again is our VM language. In the previous unit, we talked about the arithmetic logical commands. In this unit, we talked about the memory segment commands, and we are ready to move on and start talking about how we actually implement these commands and make them work for real. This will be done in the next unit. Welcome to Unit 4 in the first module of the course. This is an important unit because up until now, we've treated the virtual machine as an abstraction. And from now on, we're going to actually build it. So to begin with, let's take another look at the VM abstraction. And basically, I'm repeating the quiz that I gave you in the last unit. And in this quiz, we started with some arbitrary stack machine state. And the question was, which VM commands will implement the abstract operation static2 equals argument 1, leading to this final stack machine state? So you saw the answer. And the point that I'd like to make now is that everything that you see here is completely imaginary. It does not exist for real. And if we want to actually execute this scenario in some concrete way, we have to realize it on some von Neumann machine. So what do we have to do? Let's think about it. If you had to do it, how would you go about it? Well, first of all, you have to take these 4 memory segments, or actually we have 8 of them, and we have to somehow map these memory segments on the single RAM that is available for us. And to do it in some sensible way, right? We have to remember where each segment starts on the RAM and manage these locations and so on. And once we come up with this mapping, we have to do something with the commands, with the push and pop commands. We have to translate them into a sequence of machine-level instructions that will operate on this world that we just built on the RAM. So we have a lot of work ahead of us, but as usual, we'll do things one step at a time, and each step will be relatively simple and well-defined. All right, so in order to carry out the implementation of the abstraction, I'm going to use a technique known as pointer manipulation, which some of you may be aware of, and for some, it may be new material. So I'd like to give you a crash course in pointer manipulation.